So as Stefano was saying before, we decided to use this virtual factory data model as a central repository to connect different kind of tools devoted to the design of a manufacturing system. Here I have an example of possible different tools that can be connected together. As an example, we can have the design of production process or the mock-up or machining tools, but in this presentation we are going to show you two specific applications. The first one shown by Stefano is about the layout design, while the second one that I will show you is using a performance evaluation tool, in this case discrete event simulation, to evaluate the performance of a manufacturing system design through a generic interface. So actually, when you design a manufacturing system, you don't only need to design the layout, but actually there's something behind that defines the way the production system will behave. And basically, there are three ingredients that you need to take care about. There are the products, the processes, and in the end, the system. So actually, when you design a manufacturing system, you have some products that needs to be manufactured, and to be manufactured, each product must undergo a production process. Moreover, you need to consider a way of specifying which kind of resources are entitled to execute the process, which kind of capability they have in terms of time needed to execute the different production steps, the quality they can provide to execute that production step, and in general a set of capability that rely on the quality and the accuracy the machine can operate on some specific process phase. And in the end, you need to put together those resources to define a system when they act together to execute the whole manufacturing process. Well, every time you design a manufacturing system, it's good to have all this kind of information contained in a central data repository, because in this way you can use whatever kind of performance evaluation method to look into the repository and try to evaluate the performance of the system design. In this presentation, we will show you how this virtual factory data model can be used as a central repository to define the knowledge related to the design of a manufacturing system, and we will show how a generic performance evaluation tool can connect to the repository, understand how the system has been designed, and then provide an evaluation of that system. In this case, we will show you the application of discrete event simulation. Every time you design a system, so you start from the product, and associated to the product, you define the process needed to manufacture that product. A product process, a production process in general, is defined in terms of a set of process steps that can be sequential or can have a much more complicated set of precedence relationship, then define a sort of specific segment of the process that should be executed to have the final product. As I said before, those product steps are provided in a usually partial order, because sometimes you have some freedom of choosing the sequence those process steps are going to be executed. Well, for each process step, you usually associate a set of needs in terms of the capability needed by the resources that are going to execute that process step. It must be said that at this phase of design, you don't need to have an already existing production system. So what you do is designing a recipe. When you say, as you are doing a cake, you say that you need a certain kind of ingredients and a certain kind of tools, but actually you don't have the specific ingredients and the specific tools, but you are only providing a sort of definition, the requirements of the ingredients, of the tools that will provide you the capability of executing that kind of process step. So here, I'm showing you what we have inside the repository. We have this class type. This is called EFC type process. This is a type class defining a step of the production process. Then we have an EFC type resource, and those two type classes are joined together by a relation that says that if you want to execute this process step, you will need to have this kind of resource. Well, notice that this EFC type resource does not specify a particular class of machines. So I'm not saying that this is the type of a specific milling machine. On the contrary, I am classifying this resource in terms of the capability it has. So it's a sort of formal representation of the capability of a generic machine to execute that kind of process. From the other side, you have to cope with the physical system, and in the physical system you have real machines with some real capability, or real type of machines with some real class of capability. And in this case we have this class defining an object definition, so an actual machine within a system, and we need to specify through this relation that this kind of object is able to provide a service identified by this resource needs. So this is the way we join together the theoretical design, so the recipe we use to define the process, together with the physical part of the design, that is the specific machine we have in a plant and their capability. So if we want to have a generic representation of the design of a manufacturing system, we can consider those classes related to the production process design, while the definition of the object is related to the specific factory design. Well, in the end, when we work with performance simulation, speaking about generic process design and generic factory design is not enough, because what we are interested in is knowing the way the processes and the machine interact together within a system to carry out the manufacturing of specific products. So we want to start from this static representation of the knowledge to have a dynamic model of the system that can provide us some information related to its behaviors. So what we have is, starting from this design layer, to define a layer below where we have the occurrence of the different process steps to be executed on a real machine. So if we want to do an example, when we design an individual of this type class, we are saying that we have a specific, a general milling operation that needs a certain class of milling machines and has a theoretical execution time of, let's say, 10 minutes. But when we instantiate the individuals of this class, we are saying that within a specific system we have a specific process that I have to execute to manufacture that specific product that theoretically need 10 minutes, but in reality the duration can be more, because something different can happen within a manufacturing system or a simulation manufacturing system. Let's say a machine can undergo a breakdown, or I can have modification of the technological parameter. So this layer represents what is actually happening within a system, a real system, or in some other case within a representation, a dynamic representation of the system. That is what we are going to have when we want to use the simulation, discrete event simulation. We will ground on this definition to measure the performance of a manufacturing system And well, actually, when we deal with the performance of manufacturing system, we can have different class of key performance indicators. Usually, the most common performance indicators are the utilization of production resources. So just to know if some machine is saturated, is utilized, or stay idle for most of the time. We want to have some idea about the flow time of products, that is, how much is the time, is the duration from the time a product enters my manufacturing system to be manufactured until the time this product exits the manufacturing system because it has been undergo a manufacturing process. And we also need some more information, as an example, to the level of the work in progress, because actually when we measure the performance of manufacturing system, we are performing some economical assessment. In the field of discrete part manufacturing, that is the kind of manufacturing system we are addressing, there are two main approaches available in the literature to measure the performance of manufacturing system. And those two groups of tools are analytical models. Analytical models use mathematical symbolic relationships to provide a formal description of the system, and then solving a system of equation in an explicit or in numerical way, we can have some idea about the performance of the system. Well, actually, those kind of tools are quite powerful, but there is a drawback. That is, they are able to model a certain set of characteristics of the manufacturing system, because we are not able to describe all the different behaviors through the equations. So if we want to go much more in details, we need to use a different class of performance evaluation tools that are named simulation model, and in this case discrete event simulation model. Well, discrete event simulation model use a computer representation of the rules modeling the behavior of the system within the computer, and we use the program to simulate the behavior of manufacturing system, just forecasting what would happen if the system ran for a certain period. We will show you the utilization of simulation models, and for simulation model, for discrete event simulation model, we decided to rely on already available commercial packages. Well, sure, this has some pros, and that is we don't have to start from scratch, reprogramming what is really available in the market, and also we have stable releases, because this kind of software commercial packages are available since years, so we can rely on years and years of use to assure the stability of the software packages. On the contrary, well, we have some license costs, but we have no particular problem because we have an academic institution, and usually the software producers provide us good economic conditions for the licenses. But there is a major problem, and is that when we use this kind of tools, they rely on proprietary data model. So they have their own way of representing the data, and this is not a big issue. What is really bad is the fact that most of the times this data model is not documented. So we don't know how they represent the information, and the only available option is perform a sort of reverse engineering, try to understand the way the data are modeled within the software, and then try to match together with the way we represent the data in our virtual factory compliant data model. So we have a lot of available commercial software for discrete event simulation. We will show you the application using Arena, that is one of the most widespread discrete event simulation software produced by Rockwell Automation, and this is quite used both in the academic and industrial world. Actually, we are working on connecting together also other kind of commercial packages, but today I will show you only the use of Arena. So, how we design the software environment to perform this kind of connection. So here in the basis, you see we have a data repository that contains the design of the factory, and this is compliant with the virtual factory data model. Then on the top we have the Rockwell Arena simulation environment, and we want a way of make those two software layers to communicate together. So first of all, we need to read somehow the data within the virtual factory data model. We use a C++ library developed by IKEA that is called C++ VUF connector that provides a way of reading inside the data model and perform some query on the data inside the repository. And then we read here, and what we do? Well, first we understand how the system has been designed, and grounding on this, we automatically generate a simulation model representing the behavior of the manufacturing system within the data repository. Given this, we build this in Arena, and then we run the simulation within Arena. As the simulation is handed, we collect all the results, we analyze the result, we refresh it according to a certain way of representing the data, and we write back the result within the virtual factory data model compliant repository. So in this way, the performance evaluation, the result of the performance evaluation are available to everybody, every kind of software able to connect to this kind of data repository. So this Arena model that we developed at Politecnico is able so to access the data, process the information, generate the simulation model, run the simulation, collect the result at the end of simulation, process the simulation result to obtain the desired performance indicators, and write them back on the virtual factory data model repository. And so we use this library developed by the IKEA CNR, and we also use the ArenaCom interface, that is a piece of software available when you buy a license of the Arena software. So, as I said before, this is a main problem, and is the fact that when we decide to use Arena, we are saying that we have to cope with the way Arena model the processes and the way Arena store the information. And actually, Arena has a sort of flow-based way of defining a process. So here I have parts that are generated, then they are machined, then are inspected, then there is a sort of decision block, and then the good parts go to the finished part, and the wrong parts need to be machined again. While when we define the process in the virtual factory data model, we have no idea about which machine is going to execute the different kind of process steps. There is another way of expressing processes within Arena that is using sequences, but even in this case, when you define a sequence of operation, you have to explicitly define the station operating the different kind of process steps. Well, this is a big problem because we use a completely different way of specifying of defining the knowledge related to the process, because we want to separate the definition of the process from the definition of the manufacturing system, while in Arena you have to put them together, and they are completely joined together. So how to cope with this? Well, we try to represent the same way of defining the relationship between the process and the resources within Arena. So for each kind of process step, we have a relation saying which are all the different stations that can provide that kind of service, and we have a sort of decision layer that assign the different process step to the different station. While in this case we have a really random decision, but we can implement much more complicated policy to assign different process steps to different resources. And here we have a different part of the model when we have all the single machine available in the system. So those EFC object definitions are represented here, while all these EFC type resources are represented here. So every time a piece requires a certain service, it enters the station representing a kind of service, and then is assigned to a specific station, let's say MS04, and then he moves here. This is the physical station, and this physical station performs the actual process step execution, and then goes back and so on. So, as Stefano was said before, we stay on top of the virtual factory data model architecture, and we use Arena to measure the performance of manufacturing system. But how we want to design the layout? Well, as Stefano said before, Jove can be used as a tool to interact with the virtual factory data model repository to move the resources and provide a real design of manufacturing system. So now I finish with the theoretical part of my presentation, and I will show you an example of using Jove together with Arena to measure the performance of a manufacturing system. And what I'm going to do is consider a simple test case. We have a production line that is able to manufacture a single class of parts operating 5 different process steps. Those 5 different process steps are a drilling operation, a milling operation, well, 2 milling operations, a quality check operation, and a final grinding operation. So here I have a table representing all the different operations with the associated processing time. They are stochastic, and here I'm defining the different kind of resource type able to provide that kind of service. So, as I said before, here I'm showing the way I am defining the link between the different process step and the machines available in the system. So let's say I want to execute a kind of process step called ML02. This is a type of process. This is a general kind of milling operation that is needs the capability of a resource type called milling resource 02. So this is the definition of the process step, while on this right part of the slide I have the way I can assign, saying that a specific resource in the system can provide that kind of service. So I can say that a specific machine called MS04 is able to act as a provider of this service, or a different way of saying the same thing is saying that a class of machines, so a class called machinery element type MTC, is able to provide that kind of service. So if I use the second way of expressing these relations, it means that every time I have a machine of that type, automatically that machine is able to execute that kind of process step. And while we will use the second way of expressing the link between the machines and the processes, because it's much more general and it provides provides me a way of easily interacting with the design of a manufacturing system. So I'm starting with 5 machines. Each machine is provided the execution of a step, and then I will try to measure the performance of the system. So I consider a layout with 5 machines. Each machine operates a single process step. Then I use Arena to measure the performance of this production system design. I check the performance, and whether there is something that is not good for me, I will modify the system and then ask once again to Arena to check, to evaluate the performance of the modified design, and then so on until I will be not able to find a suitable design for me. The design of the system will be defined through Jove Virtual Factory. Here you can see the design of the production line within the Jove WF virtual environment. So we did some time before we had some problem. So if I move through the system, it's not so fluid, but actually I can navigate through the system and moving inside. But I think you cannot see the movement in so fluid a way, and so I will stay on a static way. So I have 5 machines, and I already defined in the virtual factory data model the process, and I assign each process step to each of these machines. So at present we don't have a graphical interface to specify all those information, but we are working on that, and at present they are coded using Protégé within an OWL file, or you can use this C++ library to code it. And so what I'm going to do is asking Arena to measure the performance of this system. Here we can connect to a local repository or a remote repository, so ITIA has a server sharing all this kind of repository to everybody who wants to connect with the same tools. And so I'm looking on the repository on my computer, and I choose the 11th one, and so it looks into the repository, understand how the system is, and then call Arena and automatically generate the simulation model and run the simulation model. Then I will ask to know the simulation ended, and I will go to look for the result of the simulation. So as you can see, we have 1, 2, 3, 4, 5 stations, and each of these stations represent the different machines in the system, while we have 1, 2, 3, 4, 5 of this kind of stations that represent the different process steps in my manufacturing process. So if I go and look to the results, I see that I experienced a flow time of the parts of about 0.7 hours, and if I go to the look to the how the machines behave, I see that I have 5 different machines, and here I have an idea of their saturation. So I have a percentage, say how much of the time the machine has been busy, and which is the percentage of the time in which the machine has been idle. And if I look to the result, I can easily understand that there is this machine that is the bottleneck of the system because it's been busy for 100% of the time, and so this machine is the one that is limiting the performance of my system. So let's say that I'm not satisfied about this performance and want to improve the performance of my system. What I need to do is going into the layout design, look for this kind of machine, and as an example, adding a new machine to avoid that this will limit the performance of the system. So the name of the machine is TC67H, so I'm closing this model, not saving, going back here, and let's ask to the properties, and look, the name is TC67H. This is the machine responsible of, this is the bottleneck of the system actually. So what I'm going to do is adding a machine of this type. So this is the same type of machine. I pick one of these and I put it in the system. So since I said before that all the kind of machine of this type can provide that kind of service, this machine is automatically eligible to be used to perform that process step. So what I'm doing is saving and going back to Arena and asking to evaluate once again the performance of my manufacturing system. So I call once again my tool that is looking again into the system and is launching again the system, and now we finish. If you look here, you will see that we had 6 stations instead of 5, so it was able to realize that a modification in the production system was done and is able to evaluate how the new system behaves. Now, if I'm going to see how the system behaves, I see that I have 2 machines of these types. They are not completely saturated anymore, while the most saturated machine is the last one. So if I want, I can go here and add a new machine of this kind. It's called VC650. This is the real one. I say once again, and then I ask to re-evaluate the system. Well, it's doing the same, and now you see I have 7 machines. So every time you modify the system, the performance evaluation tool is able to realize that something has changed and rebuild from scratch a new performance evaluation model that you use to measure the performance. So, well, actually we know that this is quite a simple example, but we are on that road and we are improving on that. So in the time we will be able to manage the same, we will provide the capability of to this framework to manage a much more complicated example manufacturing system. So this is the end of my presentation. I want just to say that ETS-CNR is the coordinator of this UFF project. This is an European research project that is going to finish in February, and when the project finishes, all the tools will be available to everybody. So as we said before, these tools are available within the Visionaire Consortium, so everybody wanting to try to connect his own tool to this framework is free to do this. Please contact the ETS-CNR and they will provide you the capability of accessing those repositories to establish a connection with different tools. So thank you for your attention.
May I ask a question, Marcelo and Stefano, for both? We saw a very efficient tool in order to manage the layout of the manufacturing system, and I really appreciate it because I can understand the complexity of all the organization of this kind of architecture between the virtual reality part first, but also with the simulation process under Arena, which is a very complex tool. Just to manage like this, so to control from an external part, I guess that it must be very, very difficult. Anyhow, just one question about the interest of the virtual reality part in this model. Did you observe when using it, or do you imagine some scenario where we can take benefit of a 3D visualization? Here it's just a feedback how it works. It could be quite a 2D layout, just demonstrating where are the machines, for example. What is the main benefit of 3D? And can you imagine some scenarios where, why not virtual reality case and things like that could help people to manage a complete process through the simulation of ARENA and in collaboration with the simulation of ARENA. Thanks a lot for your answer in advance.
So yes, well, first of all, there is the most common benefit of virtual reality, that is the fact that it provides you a much more realistic representation of what you are going to design. So sure, we can stay on the two-dimensional layout and we have the same kind of information that we need to provide the simulation model. So that's true. But in the end, I mean, you know that when we use a three-dimensional model, you provide the user, and I mean not an experienced user like us, but a guy that is going to design his own manufacturing system, a different way of imagining how the plant will be. So this is the basic advantage that virtual reality representation has. However, there are some more benefits that can have, and here we use the three-dimensional environment to do a really simple analysis. So designing the layout and then passing the ball to the arena that actually does not care about the graphical representation of the machines. But there are some aspects when you design a system where the three-dimensional representation is really important. Let's imagine to design the facilities you need within a plant. That is the electrical installations or the steam facilities or other kind of aspects like the space you need for the transportation system to move within the plant. Well, in that case, having a three-dimensional representation of the systems is quite important because you have a correct idea of the how your machine will behave within a plant and how your transportation system will move, and if they can colleague one with each other, or if you have enough space for a machine and a transportation system to stay in the same area. From another point of view, there are some other aspects within the design of manufacturing system. Let's say the ergonomic aspect that we are not addressing in this field, in this preliminary demonstration, that actually rely on a 3D representation of the work area of the man, and given this you can provide some feedback whether this is healthy for a man to operate in that kind of area or not. And so what we are doing is we provide a central repository. When you have all the knowledge related to the manufacturing system that comprehends the geometrical representations that is provided in terms of the shape of the machines, of their positioning in the layout, but also other layers that are the layers modeling the behavior, their behavior in the system. And given this representation, you can connect whatever you need. If you have a tool that, given the place where a human is staying, is able to check whether the ergonomics is good or not, well, you can do it unless you are able to connect to the repository. So I think that for this kind of application, the virtual reality is really important, but from the other side, it, however, provides a way of interacting that could be useful to a person that is going to design his own plan to understand how the plan is going to be.
But does it mean that you should have also some export model of your virtual reality scene in order to be able to assess some other expertise within other environments, for example, for ergonomy and so on? Maybe it will not be done in GeoReal or in ARENA, but on other model, on other plugin system or in other connected system that could be taken in charge by other partners. Why not?
Oh, yes. Well, actually, the repository is itself an export file. I mean, when you have the repository, you can connect it locally, so I can pass you the set of ontology files, and you can read it and have all the information, both three-dimensional and related to the behavior of the system. So there's no way of exporting anything because this is a repository, a data repository. It's a sort of database, but this is an ontology. On the other side, ETIA also provides a different mechanism that is connecting to a server and inquiring the server about the data. And as I told you, as I showed in the presentation, the available tools at present are some C++, well actually some software libraries that are available in C++, C#, and Java, and those software libraries are the connectors you can use to read the repository. So actually they do nothing specific, but they provide some more advanced tools. So as an example, you can perform some advanced query, say, give me back all the elements in the repository that are a machine of this type, and it gives you back the list of those machines. And then you can inquire and say, please give me back the geometrical representation of that machine. So they are basically a way of interacting in a high-level mode with the repository. So there's no problem in sharing the data because this is a data repository. The only thing you have to do is inquiring it using specific interface or specific tool. That's all.
Maybe it would be interesting also if you could give us some more insight on the criteria that you use for doing this evaluation, this productivity evaluation, so on. Now you showed us in this demonstration that you observe, given a current layout, where you have, for example, any bottlenecks. Do you use any other criteria to evaluate the performance, for example, any flexibility measurement, availability, reliability, something like that? And is there a possibility also to have some automatic suggestion from the tool, for example, for line balancing or something like that?
Well, as I said before, at present we are able only to do some really simple analysis. Well, I have to say that the simulation model is automatically generated from scratch. So this means that from scratch we build a way of modeling the behavior of the system. So what we are considering is that if you move the machines, the transportation time between a machine and the other is longer. That's the kind of analysis we are doing. And when you put a machine type within the system, automatically this machine is able to perform a certain set of operation, and Arena is able to, well, using some policy to assigning those process steps to the different machines. At present we have no tools providing different analysis like suggesting the weight of modifying the system to have a better performance, better behavior of the system itself. Well, actually, what is important is, however, that we are not adding any knowledge within Arena to allow the simulation model to be defined. So this means that all the information about how the system behaves are embedded in the repository. This means that if you use whatever kind of tools, another simulation tool or a different performance evaluation tool like an analytical methods, and if you look in the repository, everything is written there. So you have all the information to know how to build the performance evaluation tool. So nothing has been added by our mind in Arena to allow the simulation model to be built. So also the key performance indicators, so what the kind of performance we want to have back from the performance evaluation step, they are already defined in the repository. So when you look at it, you already know what you have to provide if you have a simulation tool or a performance evaluation tool. Maybe you will not be able to provide all of them, but you know all the requests. Okay, and this is really important because we are detaching the knowledge from the tool you are using. Okay, and well, I wanted to say something else. Well, once you have these performance evaluation tools, you can use together with other tools, let's say an algorithm for looking for the best solution, because, well, optimization algorithm grounds on a way of measuring the performance. So it's an easy step to add another tools that grounding on the result of the performance evaluation decide how to modify it. I repeat, at present we are at this first stage. However, I want to add that we are working in an industrial project together with the Italian industry, and we are providing them a way of designing complex plants using this kind of three-dimensional environment. So they move the machine, they define how the system, how are the components in the system, and then I use this kind of layout definition to instantiate a model. The difference that since the system is much more complicated, I'm not able to generate the simulation model from scratch, but I have an already defined simulation model, and I only tune it according to what the user define, how the user define the layout. So the difference is that as the characteristics of the system are much more complicated, we are no more able to generate the simulation model from scratch, but given already defined reconfigurable simulation model, we can set the freedom, reconfiguration freedom according to what defined in the layout. So, well, this is the path we are defining. It will take some time because it's quite hard to merge together these two aspects, but I mean, we are working on that.
So in this ontological representation that you have, do you already have created some representation, some classes also for these performance indicators? Not only, I mean, that you have some machines and they have some properties, but you also have developed representations for multiple performance indicators, such as the ones that I mentioned before.
So that's true. This is another quite complicated area, and at present we have some really simple performance indicators as the one I showed you before. So every time you define a resource, you automatically have a statistic, so a performance indicator associated, that consider the states in which the resource has been during, I mean, it could be connected to a real system or it can be connected to a simulation model, but, well, the most simple kind of performance indicators you need for a machine is knowing how much time it was busy, how much time it was idle, how much time it was failed, and if it was failed, which kind of failure did it had. So this is the simple thing you need, but this we have already. And for another kind of performance indicator we have is related to the time performance of the execution of manufacturing process. So every time you have a manufacturing step, you have a time, this is the theoretical time, and then you have an actual execution, and then we have a way of collecting the actual execution time for all the process steps. And then you can compare it. You have a statistic, say that on average it took 10 minutes to perform this kind of process step, and then you can compare with the theoretical one. So those are the two classes of performance evaluation already available. So a sort of statistics about the states of the machine and in general of the resourcing, and a time analysis of the execution of the process steps. Well, actually also there some more work is needed, because you can define whatever kind of performance evaluation, and we will need a way of being able of specifying it within the data repository.
Can you imagine that the result of the simulation could be interpreted and presented through GeoVe, the virtual model? For example, some semiotics with colors or figures appearing on the machines, for example.
For the overloads and things like that?
Yeah, or the flow of the parts, because I know that Arena is able to model that kind of things. So this could show the interest of having a 3D model in order to visualize the bottlenecks when parts are waiting for machining, etc., for example.
So actually that's the final objective. So it would be nice to have also the result presented in the Giove. IKEA is working on that. Maybe Stefano, I don't know if he's informed about that, but they provide now the capability of showing a restricted set of results within Giove. Well, this is really simple. You see a window that is opening with some result saying that this machine has been busy for that percentage of time. Well, actually I want to say we can do that, but at present it's not general. I mean, our aim is that if you define some performance in the data repository and you have a software that is able to visualize this performance, whatever kind of performance should be self-defined. So just looking in that, you should be able to represent it. At present we can do that, but it's hard-coded. So we say we coded within Giove that we want to show that, and we said it that we have to go there to look for that statistics. So yes, we can do that. But, well, if we look at the fact that our aim is having something really general and that provide full interoperability, we are not yet satisfied, I would say. But, well, for a simple set of statistics, we are already able to do that. I don't know if Stefano has a demonstration of that, but we can do that.
Okay, thank you. What I had in mind, in fact, was to use Giove as the only interface to the simulation, the layout, the building of the layout, and the simulation of the system. And that was what I had in mind.
Yes, even if from our experience, this will not be the final solution. Because if we look for the design of the system and to have some information about the performance, I think that this kind of interface is really useful because provide the user a really full experience of understanding what is happening in his system. But as we are experiencing the definition of the process, as an example, while three-dimensional environments are not performing well. So in the industrial project we have two interfaces. An interface where the user describes the process, and this is a plain interface, a two-dimensional interface when you put inside the blocks define the process, and then you use Giove just to move the machine. So in our opinion, for the layout and for the statistics, that is a quite good tool, but if you want to perform different operations like defining the process, a two-dimensional interface can perform better usually.